Hello, greetings to you and welcome back to the second part of this class. Okay, we stopped at understand the aspect ratio. Now, when we talk about aspect ratio, basically we are looking at the relationship between the length of the longer side of our slab panel and the shorter side of our slab panel. Now, for example, we have a panel in this manner. Let's say we have this in this manner. We have 1, we have 2, we have 3. Okay. Now, under 2, we have say 6 meters here. We have 3 meters here. Okay. Now, for us to understand our aspect ratio better, if we are considering panel 1, it means that the length of longer side will now be ly. In this case, it will now be 6 meters. Okay. Now we have the length. We have length of shorter side. Okay, length of shorter side, which is Lx, which will be 3 meters. So this is the consideration for panel 1. Okay, if you look at panel 1, the length here is 6 meters, the width here is 3 meters. Okay, so we have length of longer side, which is our Ly, is equal to 6 meters, while the length of the shorter side, Lx, which is 3 meters. So the relationship between the Ly and Lx is what we refer to as aspect ratio. Okay, and we usually adopt our aspect ratio where we want to define the case that this particular panel, okay, satisfied, because there are different. We have case 1, we have case 2, case 3. Okay, all of these are different conditions of our slab panels. That is why if you look at case 1, if you look at panel 1, it's quite different. The orientation in terms of the boundary condition is quite different from panel 2 and panel 3. Okay, so each of these panels satisfy different cases. Okay, and it is your aspect ratio that you can be able to obtain the moment coefficient from the table, which you use to design your each of those panels. Okay, in most cases, in two-way spanning slab, okay, you obtain your moment from your moment coefficient table. So that is the aspect ratio for you. So once you have done that, the next you're going to do is to determine the effective depth. Okay, you are determining the effective depth of slab D. Okay, so that is the effective depth of slab. Now, for you to calculate for the effective depth of slab, it means that you have your D is equal to H minus C minus D over 2. Okay, D over 2. So what this simply means is that, for example, you have a section of your slab in this manner. Okay, you have a section of your slab in this manner, and you have your reinforcement. Okay, you have your reinforcement. All right. So from this point to this point becomes your H. Your H. Okay, becomes your H. All right. Then from this top to half of this reinforcement becomes your D. Okay. So then this point to this point okay, becomes your CC. Okay, becomes your CC. Alright, so for you to get the effective depth, it means that you have to deduct, this is a concrete cover, CC is a concrete cover, YD is the diameter of your rebar. Okay, this is the rebar, so half of the diameter, that is, if you have your diameter, if you have your reinforcement this way, half of it, okay, half of it is what we are looking for. So half of it falls under the effective depth. So you have to deduct that. All right. So when you deduct that, you have your overall depth minus your concrete cover minus your depth. That is, sorry, your diameter of reinforcement D divided by 2. So when you work that, that becomes your effective depth. Okay, that becomes your effective depth. All right, and it's usually in millimeters. Okay, usually in millimeters. All right, so once you are done with this, the next you're going to do estimation. You do estimation of loads, estimation of loading, estimation of loads. Okay, now this estimation of load here talks about your permanent action, okay, and your variable actions. Okay, so in this context now, you under your permanent actions, you consider the self-weight. Okay, you consider the self-weight of slab. Okay, you consider the finishings. Okay, the finishings. You consider unknown partition allowance. Okay, now the finish in this context has to do with, you know, those your terrazzo finishings, your tile finishings, and all of that. Okay, those are under finish. I just categorize them as finishings. So the unknown partition, I've discussed that in our previous class, so I believe you understand that. So when you have all of this, it becomes your GK. The summation of this becomes your GK. Okay, so your variable load now is usually for residential. Okay, for residential we have it as 1.5 to 2 kilonewton per meter square. So ideally it's better to adopt the higher value. In this case, it's better to adopt 2 kilonewton per meter square as your life load, that is variable action. Okay, so once you are done with this, the next you're going to do, which is our 7, is to calculate. Okay, you calculate for the ultimate. You calculate for the ultimate design load. Okay, you calculate for your ultimate design load. All right, and for our slab, we usually consider it as a simply supported, okay, with a uniformly distributed load, because we are treating the panels. Now understand that as you're treating the panels, your emphasis should be at the shorter side, because that is where the main bar is expected to run. Okay, the bottom bar is expected to run across the shorter span. So your emphasis of designing is to design for the tensile reinforcement, and your bottom bars are mainly for tensile forces. Okay, so for you to calculate your design load according to Hero Code, we have it as W is equal to 1.35 GK, okay, plus 1.5 QK. Alright, and I have told you previously that your GK is your dead load. Okay, is your dead load, the summation of this. Alright, because these are permanent load on that on that slab. So that becomes your GK, the summation of all of this. Then your QK is, if you are adopting 2, so it becomes 2 here. So when you work out this, that becomes your ultimate design load. Alright, so you take note of that. So once you are done with that, the next you're going to do is to determine the design moment. Okay, you determine the design moment. Alright, because you have to look out for the moment that is generated on that slab unit. Okay, so for you to determine the moment, in this context, we can adopt M as equal to WL squared over 8. Okay, so this becomes the moment, the maximum moment, because we are looking at the maximum moment that will be generated at that short span. Okay, because our emphasis is mainly on the short span. So the maximum moment there is WL squared over 8. Now our W is what we calculated as our ultimate design load. Why our L becomes the span. Okay, the span. So in this context, if you're designing panel 1, it means that your L now becomes 3 meters, which is the shorter side of the panel. So that becomes your L squared over 8. So when you substitute, it becomes the moment. Okay, it becomes the moment that is generated on that slide. Alright, so once you're done with that, the next thing you're going to do is to calculate the K value. Okay, you calculate the K value, and your K value is equal to your moment divided by BD squared, okay, FCK. Alright, now FCK is the characteristic strength of concrete. You can, in BS code, is usually FCU. Alright, it's usually FCU, but in Euro code is FCK. So take note of that. So your K value now has to do with your moment divided by your B. Your B now becomes the breadth of your slab. Okay, because in slab we consider per meter run, which is 1 meter run. Alright, so in this case, the 1 meter will be converted to millimeter. It becomes 1000 millimeters. So that is what you substitute here for your B. Then your D now becomes the effective depth that you have calculated here. That becomes your D. Then the FCK, like I said, is the characteristic strength of concrete. So before you design, you must have come up with a certain, strength of concrete for the slab. If it is 20 Newton per millimeter square, you have to substitute 20 for FCK. If it is 25, you have to substitute FCK for 25. So once you have done that and you calculate, it's important that whatever you have as your K, if it should be less than 0.167. Whatever you calculate here should be less than 0.167. Alright, so if it is greater, it means that this cannot sustain. Okay, it means that this cannot sustain. So in most cases, it means compressional reinforcement will be needed. Okay, it means that compressional reinforcement will be needed. And compressional reinforcement are usually at the top. Alright, when you have a flexural member in this manner, if you have a flexural member in this manner, these are imaginary lines separating. So we have the upper zone, we have the lower zone. Okay, then this is the upper, we have the upper zone. Okay, we have the upper zone. Now this usually is in tension. The lower zone is usually in tension. Okay, while the upper zone is usually in compression. Okay, so we try to design for tensile reinforcement. Alright, so in the case where the K value here is greater than 0.16, it means that there is need to also provide reinforcement at this upper zone. Remember, our slab now, usually this K value, okay, has to, if it is less than this, it means that your emphasis should be on this lower zone, which is the tensile, the zone under tension. Alright, so once it's less than, the next thing you're going to do is to calculate the lever arm factor. You calculate the lever arm factor, LA, and our LA is equal to 0.5, okay, plus square root 0.25 minus K over 1.134. So this is what is provided in our hero code. Okay, this is what is provided in our hero code, and it states that when our LA is greater than, once it's greater than 0.95, okay, the code says use LA equal to 0.95. Okay, that is what the code says. Okay, that is what the code says. Once it's greater than 0.95, once you calculate your LA, okay, and it's greater than 0.95, the code says you should use LA as 0.95. That is, if you've calculated and you got 0.96, okay, you don't use 0.96 for your LA, you use 0.95. But if you've calculated your LA, your lever arm factor, and you got 0.94, it means that you have to use that 0.94 as it is, okay, because it's less than 0.9. So that is what that is what is being provided. All right. So once you're done with this, so let me wipe off this section so we can continue. Okay. Let me wipe off this section. All right. So once you have calculated your lever arm, okay, let me also wipe off this section. Okay. Let me also wipe off this section. Okay, so once you have calculated your lever arm factor, the next you're going to calculate now, you determine the lever arm. Okay, you determine the lever arm, and your lever arm here is Z. Okay, and Z here is equal to your lever arm factor multiplied by your effective depth. Okay, so it means that your lever arm now is your lever arm factor multiplied by the effective depth, which is what you have gotten here. Okay, that becomes your lever arm. Alright, so after you have calculated your lever arm, the next you're going to do is to calculate the area of steel. Okay, you calculate for the area of steel. Alright, now remember, our design basically has to do with mainly the reinforcement aspect of it. Okay, because the concrete is also considered in design, but the end product of our design is the reinforcement. Okay, because that is what gives the framework, okay, of every building, the skeletal framework of every building. So the area of steel will now be area AS AS, okay, required, is usually termed as required, is equal to our M divided by 0.87 FYKZ. Okay, so this is what is provided by Hero Code. Okay, this is what is provided by Hero Code. It means that we have our moment, okay, moment divided by 0.87 FYKZ. Okay, so 0.8 is a constant, while we have FYK means the strength of your steel. Remember, before you design, you adopt a certain strength. Okay, so that is why what we are doing here is also to give you idea when you're using your software. Okay, your design, any of the design software, is important that the strength of these materials must be considered. Okay, there are some cases where you have default provisions. Okay, you might have 500 Newton per millimeter square as your default for the strength of reinforcement. It is important that if the strength of reinforcement in your location is below 500, you don't design with that default provision. Rather, you change the strength of that provision to the strength that you are adopting. If it is 410 Newton per millimeter square, you substitute that for your FYK. All right, so your FYK becomes the strength of reinforcement. So if it is 410, you substitute FYK for 410. Then your Z becomes your lever arm. Whatever you get from here is usually in millimeters. Okay, is what you now substitute for your K. All right, so when you now calculate for this, you now get the area of reinforcement per meter run. Okay, you get the area of steel, usually millimeter square per meter run, because you're considering per meter run. Okay, so once you have calculated this, the next thing you're going to do is that you now provide reinforcement or rebar spacing. Okay, you provide rebar spacing. All right, you provide rebar spacing. Now understand that for you to provide your rebar spacing, which you're going to see as we progress in the course of the class, how you're going to provide. Understand that this area of steel that we have calculated is usually what we need to provide for a higher area of steel. So there is a table for spacing. Now that table constitutes the diameter of bars, vertical part of the table, the top horizontal has to do with the spacings of this reinforcement, while the main body of the table constitutes the various area of steel provided. Remember, what we have here is area of steel calculated, but the table gives us area of steel provided. So it's important that when you have calculated your AS and you go to the table, you look for AS that is higher than the one that you have calculated. Okay, so that will now aid you to now trace the spacing for that diameter of reinforcement that you have used to design. Remember, when you're calculating the effective depth, you consider the certain diameter of rebar here. So that diameter is what you now use as a reference point, okay, to trace area of steel provided that is higher than the one that you have calculated here. The value that is higher than the one you have calculated here, then you trace vertically to get the spacing for the reinforcement. That is the spacing, how you're going to place this diameter of bar on the slab, how you're going to place it center to center. Okay, so that is provide river spacing. So at the end of each design for the panels, you have to provide area of steel. Okay, but while you're providing now, you don't include the number of the reinforcement yet. Okay, all you need to do is to identify the strength of the steel that you're using. If it is high heel steel, if it is mine steel, and I told you the notations that we use to represent our mine steel and our high heel steel. So you state that strength of the strength of steel, then you state the diameter. So for example, you can have let's say H12, okay, at 150, okay, cc. Then you place the area, okay, the area for this that you have provided from the table, okay, you place the area of 150 millimeter spacing in front here. So whoever that sees that area will know that that is the provision for 150 spacing, center to center. So this is what you have to present as your end point for the design of each of these panels. All right, so that at the end of the day, you are going to now extract all of these details, okay, and now go further, which is what we refer to as detailing. So you see the relationship between our analysis, design, and detailing. These are sequence of our design. Okay, so it is after we have done this design, then we now proceed to detailing. So detailing is an integral part of the process. So all the outputs you've got from your design, you're going to now shift it to the detailing aspect, where you are now going to produce your slab drawing and now present all of these details in that slab drawing that you have made. You now show how the reinforcements are spanning with their various information that you have gotten from the design. Okay, so basically these steps you are going to repeat it for every of the or rather from this point, let's say from this point now is what you now from 8 down, okay, from 8 down this way, you're going to have this for each of the panels that constitute that slab, because you can have this uniformly distributed on that slab, the load, okay, the moment too, okay, no, the moment, no, you start here, you start from your moment, because remember the span is what influences the moment, okay. So because you know the moment, maximum moment is being experienced at the mid span. So if you have a span of 3.6, okay, it's quite different from a span of 4 meters or a span of 4.5 meters. So so you see that the span influences the moment that will be generated. So from this point is what will now change, you know, in other panels that constitute that slab. Okay, so this is how you're expected to go about the designing of your slab. So this is just the procedural approach, okay, in the design of our slab. Now understand that before you start off this, you can do a grid sketch of the floor plan. After you have studied the architectural plan, you can do a grid sketch of the floor plan. All right, now that grid sketch will provide the spans. Now understand that when you're doing that grid sketch, the dimension will change. It will no longer be the way it is on the architectural drawing, because in the architectural drawing, the dimension is taken from in to in. All right, it's taken from in to in. What I mean in to in, from the inner surface of the wall to the inner surface of the opposite wall. That is the measurement for the architectural drawing. But when you're doing your sketch, your gridding sketch for the design, you have to do it grid to grid. It means that half of that wall, half of the wall on one side to the other half of the wall on the other side. So what it means that you have to, if you have a 3600 millimeter in to in on your architectural drawing, it means that you have to take half of the wall on one side and half of the wall on the other side. Okay, then add it to the 3600 millimeter. That becomes the span from that grid on one side of the wall to the other grid line on the other side of the wall. So that becomes the dimension that you're expected to work with when you're doing your design. Okay, you don't use the dimension on the architectural drawing directly. Okay, you have to do your grading. Okay, you have to do your grading. You do a grading, dimension that grid. That is when you can now start your design. And when you have done that grid, your sketch with the grids, then you can now do your paneling. All right. Now your paneling now will now show the nature of these various individual panels that constitute that slab. If it is a one-way spanning slab, if it is a two-way spanning slab, and that is as a result of the spans, the dimensions that are provided. Okay, we are going to also, as we go further, we're going to see when a slab is a one-way spanning slab and is two-way spanning slab. We'll get to see all of that as we progress. Okay, but this is mainly the procedure on how we're expected to carry out our design process. Okay, this is according to Hero Code. Okay, this is according to Hero Code. Okay, this is according to Hero Code. Remember, I told you we also have BS code, you know, for our design, but currently Hero Code has, you know, replaced BS code. So this is a provision for BS code. Now understand that for this is a factored load that I told you before. Okay, and in this case we can consider it as unfavorable. All right, we have some cases where we consider the permanent and the variable actions as favorable and unfavorable cases. Okay, but this provision is for favorable. All right, this is for favorable case. Okay, and it's a factored load, so we consider this for our ultimate design load. All right, now understand, by the time we get to to talk about the one-way and two-way spanning slab, you will find out that is where for us to design and for us to design a two-way spanning slab, it means that we need a moment coefficient table, and that is where this aspect comes in, the aspect ratio and the boundary condition. Okay, we also see this, okay, because you need two of these to be able to extract the moment coefficient, okay, that you use to design that particular panel. All right, so as we progress, we're going to see all of that play out. Okay, so understand that this is just the steps that we need to follow. Okay, then there are some cases where you might have different loading conditions. Okay, in terms of the ultimate design load, you see the variation. All right, so you have to treat those panels based on those variations. Okay, but if there are no variations, this ultimate design load is applicable because it's per meter run. It's considered all through the area of that entire slab. So any of the partitions that you're designing, you design with this ultimate. You design that panel based on this ultimate design load. Okay, so basically, like I said, this is the steps that we need to follow, in designing our RC slab. All right, so if there's any question as regards to what we have discussed so far, you can send them across for further clarification. Thank you very much, and do have a wonderful day. Bye.